Welcome to the ET380 lecture video on satellite communication. Okay, let's talk about some basic satellite terminology. A circular orbit would be circular path around the Earth. The sub-satellite point, or the SSP, is the point on the Earth directly below the satellite. The satellite period, or the sidereal period, is the time it takes for the satellite to orbit the Earth. Okay, here's an elliptical orbit, which is an elliptical path around the Earth. The geocenter is the center of the Earth. Here's elliptical orbit again. This is the geocenter of the Earth, and this is the perigee, and it is the short side, and apogee is on the long side of the ellipse. Okay, here's a geosynchronous path, and this is in red. And it's a satellite around the Earth, a period that's equal to the Earth's rotational period, around 23 hours and 56 minutes and 4 seconds. And it's approximately 22,236 miles above the Earth, and appears to move across the sky as the Earth rotates. Here's a geostationary orbit, and it goes around the equator. Okay, geostationary orbits are circular and they're directly above the equator. It has no inclination. It's approximately 22,236 miles above the Earth. Has no eccentricity. Located directly above the equator. Stays fixed over a single point on Earth. Appears fixed in the sky to ground observers. Ideal for applications like satellite television and telecommunications. Here's some breakouts of satellites. Low Earth orbit. Its orbits relatively low altitudes, 160 to 2,000 kilometers. It completes an orbit quickly, about 90 to 120 minutes, and it's used for satellite internet. Medium Earth orbits, MEOs, are altitudes 8,000 to 20,000 kilometers. It's used for navigation in systems like GPS. Geostationary orbits, they orbit a fixed point above the Earth equator, appearing to stay in the same position relative to the Earth, and it's used for broadcasting, telecommunication, weather monitor. And we have approximately 600 geostationary satellites. So satellites are used for telecommunications, broadcasting, data communications. So active versus passive. Active satellites amplify and retransmit the signals. Passive satellites simply reflect them. Radio frequency RF versus optical. RF satellites use radio waves, and optical satellites use lasers for communication. And here's a picture of a satellite and its basic systems. So it has an antenna, orientation and propulsion system, batteries, a transponder, and solar cells for powering. GPS satellites are located in 6 orbital planes, all at an angle inclination of 55 degrees. GPS satellites are in medium Earth orbit, around 20,200 kilometers, or 12,550 miles. And the period is 2 orbits a day, or approximately 12 hours. Here's an animation of satellites, GPS satellites particularly, and as they grow over the years. So this is between a period of, looks like 2013 and 2018. In order to find a location on the Earth, we need at least 3 satellites to triangulate and find the position that we're looking for. We need the 4th satellite is required for finding the elevation. So we need 4 satellites in order to get a position. Since we're talking about satellites, let's take a look at space junk. 1957, clear. 92, pretty heavy. 2015, look at the mass amount of trash and debris we've left up there, and at 2025, you can imagine. The U.S. is not the only one with GPS-type navigation satellites. So the U.S. is called GPS. We have 31 satellites. GLONASS is Russia, and they have 24 satellites. And we have Galileo, which is the European Union. They have 24 satellites, and they're targeting for 30, which they may already have hit. And the BDAO from China. Okay, the main uses for GPS is location, navigation, tracking, mapping, and timing. In order for GPS to work, we have to have very, very accurate timing, which we could also utilize. Here's a diagram of navigational satellite frequencies, and it's breaking it all down. And in the United States, we have a L1, L2, and an L5 band. Okay, the GPS L1 band is at a frequency of 1575.42 megahertz. It carries the coarse acquisition code C/C and the precise P code, which is military use only. And it is more accessible and widely supported by GPS receivers. Its signal can be affected by obstacles and interference. GPS L2 has a frequency of 1227.6 megahertz. It carries military codes P, Y, and a civilian code L2C. L2C offers improved accuracy and signal strength, making it better penetrating obstacles like buildings and trees. Okay, the GPS L5 is a frequency of 1176 megahertz, and it's used for safety of life or transportation, other demanding applications such as aviation. And because of the higher power and the frequency, it's able to penetrate deeper and eliminate obstacles from damaging the signal. Here's a diagram of a transponder, transmitter, receiver on a satellite. So we have receiving antenna, low noise amplifier, an LNA, down converter, intermediate frequency as a bandpass filter, RF pre-filter, and a high power amplifier. And these frequencies usually are different between receiving and sending. There's a diagram of a uplink coming from source and a downlink from the satellite to the ground. Differential Global Positioning System, or DGPS. It's a method of improving the accuracy of the GPS location. It's used in construction, surveying, navigation, and agriculture, where we have a fixed location that we've surveyed and we know, and we put in a device with a transmitter, receiver, and computer. It takes a signal from the GPS satellite and calculates it and changes the corrections and sends that to our location of the GPS, and it improves the accuracy. Okay, let's look at satellite tracking. We have a website, n2yo.com, that allows us to track satellites, and it gives us a lot more information, and it's a good tool. Here I am showing this is a ham satellite, ham radio, and the reason I chose this one is it's going to buzz right by my location in LA. And yeah, here I am showing the International Space Station travel, and it's showing the day and the night times. And there's our space station. Okay, here I'm at the website, and we're tracking the space station. It is not near us at the moment, so let's go ahead and find, how about we try the weather satellite, and it gives us all the information about where it's at. Its NORAD ID is international code, and its location and when it was launched, and what communication channels it uses. So let's go ahead and use satellites on orbit, and let's go ahead and find a amateur radio station. And what I do is I look through here, and I need it to be active, so I go ahead and click active or status, and I get active. And I look through here, I want it to be uplink communication, so I want to talk to this satellite, and I'm going to use ISAT-1. And here we have that satellite. And what I'm going to do is go ahead and use 10-day predictions. And I'm going to look for a dark gold stripe. And this one's going to go right by San Francisco and Los Angeles. And it gives me the channels that I could communicate with us. And I know what time it's going to be passing my location, so I could utilize information in order to talk to it. In order to communicate with the satellite, we need to know the information. We have to have a ham set up, and we need a directional antenna. And I found this directional antenna on Amazon. And we could utilize the information we find from the website to find its azimuth and direction, and we could communicate with that satellite.